Hey everybody, Mr. Murray here on Mr. Murray's Mathland, and today we are talking about a classic rule, very cool, L'Hopital's rule for limits. And specifically, it is for what we call indeterminate limits. Limits of indeterminate form, generally 0 over 0. That's the classic one we've encountered a lot at this point in calculus. Also, plus or minus infinity over plus or minus infinity, that's also indeterminate. There are some other types of indeterminate forms too, like 0 times infinity, because that literally you can't determine without some further work. But the two we're really going to focus on are the 0 over 0 and infinity over infinity type. That's the two you're going to encounter at this level, most frequently. 0 over 0 in particular is what this video is going to focus on. So here's what L'Hopital's rule says. If you are trying to take the limit of a quotient f of x over g of x, if the limit of the numerator is 0 and the limit of the denominator is 0, and that's just a fancy way of saying you get 0 over 0, but more on that in a minute, or if the limit of the top is plus or minus infinity and the limit of the denominator is plus or minus infinity, that's also indeterminate. And if either one of those things is the case, then the limit can be arrived at by taking the limit as x approaches the same number of the ratio of their derivatives, f prime of x over g prime of x. So notice that is saying, take the derivative of the top and derivative of the bottom, not the derivative of the fraction, and do a quotient rule and all that. Okay, so let's just jump into using this on a problem here. So you know that by this point, trying to take the limit as x approaches 1, your first move would be, let me just try direct substitution. So ln of 1 is, of course, equal to 0. That's saying, right, e to what power gives you 1, and that would be the 0 power. So you get 0 up top. If you substitute 1 in the bottom, you get 1 minus 5 plus 4. That's going to give you negative 4 plus 4. That's also going to give you 0. So this is a 0 over 0 indeterminate type. There's no factoring to be done that can help you like we did in the beginning of the year. So this is when L'Hopital's rule is great. However, approaching this from an AP, College Board standpoint, if you're about to use L'Hopital's rule, you have to justify that it can actually be applied. And that means, playing the game and formally presenting the argument that you understand the conditions to be met. So if you basically just polish up what we just said. Oh, the limit of the top is 0, the limit of the bottom is 0. So I'm just going to show that. The limit as x approaches 1 of ln of x by itself, the numerator, is equal to ln of 1, which is equal to 0. The limit of the denominator, notice how I'm writing a separate limit, is equal to 1 minus 5 plus 4, which is equal to 0. So you have shown the limit of the top and bottom each equals 0, and so you can now say L'Hopital's rule applies. By the way, you may see in some textbooks an alternate spelling L'Hopital with the S, spelled like hospital, or you see the traditional French there with a little circumflex over the O. If you don't write the little circumflex accents, no big deal. I don't think, at least. So we've shown that L'Hopital's rule applies. So now let's actually use it. And that means I can show that this limit I'm trying to evaluate is equal to this limit. As x approaches 1 of the derivative of the numerator, ln of x, is 1 over x. Easy derivative. The derivative of the bottom, that's straight power rule, 2x minus 5. And now, try to evaluate that limit. And what's our first move? Direct substitution. And directly substituting 1 in for x isn't going to yield any sort of undefined 0 over 0 indeterminate kinds of quantities. That's going to be 1 over negative 3 or negative 1/3. And there we go. Very cool, right? All right, so let's just try one more here. And notice this one may look a little more complicated, but it's all essentially the same thing. So, imagine you were, approaching this. It was in the middle of a whole big test, and you hadn't done L'Hopital's rule in a while. First thought would be to try to plug it in, and maybe you start to, take a good look that this is going to be e to the 0, which is 1, plus 0 minus 0 minus 1. I'm going to get 0 up top. And then you really got to be on the high alert. Okay, if I get 0 on the bottom, this is going to be a L'Hopital, and I got to show it before I use it. But in the bottom here, sine of 0, that's going to be 0 minus 0 minus 0. That's going to be another 0 on the bottom. So here we go. Let's just show it. You don't want to lose points. And they make a big deal out of this, by the way. And L'Hopital's rule was sort of added to the AB curriculum, I don't know, 7, 8 years ago. And since then, the graders have said that students often mishandle it, or they lose points for doing things like this, saying this limit equals 0 over 0. They have a big problem with that. That's called linkage errors. And this limit doesn't equal 0 over 0 because 0 over 0 is an undefined quantity. So the limit doesn't equal an undefined thing. So just take care not to do that. You might think it's kind of picky, but hey, you know what you're doing. Get the credit you deserve. Do it the right way. Polish it up. So the limit of the numerator, write two separate limits. The limit of e to the 6x plus 2x cubed minus 6x minus 1. And if you've already done all the substituting in your head, you know that that is 0. You don't have to actually show all the plugging in if you are sure. And the limit of the denominator, the limit of sine of 4x minus x squared minus 4x as x approaches 0, as we've said, is also 0. So we can say from that, L'Hopital's rule applies. So let's use it. Here we go. So this limit is equal to this limit. And they do like to see this, I believe, this new limit written out with those two derivatives before you try to do too much and substitute. So again, show the steps a little bit. Try to play the game. E to the 6x, the derivative of e to the 6x is e to the 6x, but then you've got a little chain rule there, so you got to multiply by 6. So that's 6e to the 6x. The rest of it is power rule, so just be careful. Derivative of 2x cubed, 6x squared, minus 6, and the constant negative 1 drops out. And then in the bottom, the derivative of sine of 4x, the derivative of sine of something is cosine of that something, 4x, and then multiplied, another chain rule, by the derivative of that, which is 4. So a little chain rule and a little trig and e review in here, and then power rule the rest of the way, minus 2x minus 4. Okay, so now we take a look at this new limit to evaluate, and our first move is let's try to substitute that in. But if you start to get a sense of how this is going, if you plug 0 in there, you're going to get e to the 0, which is 1, times 6. You're going to get a 6 plus 0 minus 6. You're getting 0 on top, so you better start to get a little suspicious here. And in the bottom, 4 times cosine of 0. Cosine of 0 is 1. So that's 4 minus 0 minus 4. You're getting 0 in the bottom again. So it's still indeterminate, but that just means you can use L'Hopital's rule again. But again, before you do it, you got to say it. So let's just show the limit as x approaches 0 of 6e to the 6x plus 6x squared minus 6 is equal to 0. And the limit of the denominator as x approaches 0. 4 cosine of 4x minus 2x minus 4 is also equal to 0, and that just shows L'Hopital's applies again. So that means we just keep trying to evaluate this limit. This one we have to go 2 layers deep at least until you don't get an indeterminate limit anymore. So derivative of 6e to the 6x, so again you get that e to the 6x, but times another 6 because of another chain rule, so that's going to make 36 as your coefficient, plus 12x, and that negative 6 drops out. And in the bottom, the derivative of cosine of 4x would be negative sine of 4x, but multiplied by 4. So that's going to give 16 as your coefficient. So negative 16 sine of 4x minus 2. And now let's take a look. Do we get indeterminate again? If you plug in 0, you're not going to get 0 on top. You're going to get something other than that. So let's go here. So let's go. Let's just keep going with this one. 36 e to the 0 plus 12 times 0, 0. I didn't really have to write that. Minus 16 sine of 0 minus 2. And yeah, not going to be 0 in the bottom either. So we are going to get 36 on top, right? E to the 0 is 1. And sine of 0 is 0. So 0 minus 2, negative 2. And we get negative 18. And there we go. So that was an example of having to use L'Hopital's twice. And occasionally that happens. I doubt you'll really see a problem on the AP exam where you got to go more than 2 layers deep, maybe 3. But, hey, just keep going, showing the work every time you use it. And, fun little tie-in back to the beginning of the year here, that now this could be used to prove or evaluate any of those indeterminate limits that we used factoring for, or conjugates to rationalize the numerator, or this special trig rule, remember, where we verified it with the squeeze theorem and we just kind of said, all right, now you got to know it. But that's where you get sine of 0 over 0, which is indeterminate. But if you use L'Hopital's rule, now you don't have to just remember what it is. Take the derivative of the top, you get cosine of x. Take the derivative of the bottom, you get 1. And now you substitute in, and you get cosine of 0, which is 1. And that was the special trig rule. So this L'Hopital's rule can be used for a lot of old limit rules too, if your factoring is a little shaky or some of these trig rules. So it's a very cool rule as long as it applies. It doesn't apply to every limit, just indeterminate ones. Okay, so that's that. If you got any questions, hit me up, and keep working hard and loving and learning limits, kids.